Now the next calculation that the students need to know how to do is called percent ionization. It's another method to assess how strong the acid is. The higher the acid ionizes, the stronger the acid. Now the percent ionization of a weak acid decreases as the concentration of that acid increases. So that's an inverse relationship. So if you look at the formula to calculate percent ionization, it's just the part that dissociates divided by the initial concentration of the acid. So in other words, you're taking the X value from your ice box and dividing it by the initial concentration of the acid. And then you have to change it to a percent by multiplying by 100. So we're going to calculate the percent ionization from the previous example. We have our X value, which was 1.21 times 10 to the negative fifth, and we divide that by the initial concentration of the acid, which was 0.3, and you only get a percent ionization of 0.00403%. Now, if we increased the hydrogen, or if we increased the acid's concentration from 0.3, let's say, to 0.6, then your percent ionization would actually go down. You would make the weak acid more concentrated, but the amount of hydrogen ions that would actually get into the solution decreases. Now there's some other acid facts that we quickly go over on the next slides. If you know the Ka value and the Kb value, you multiply them together, you get the Kw. So every weak acid has a Ka value, and so if you wanted to know the Kb of the conjugate base, you could determine that by using this little formula. So the Ka of an acid times the Kb of its conjugate base equals the Kw, which is 10 to the negative 14th. Now, as the Ka value goes up, your acid strength goes up. As the Kb goes up, your base strength goes up. If the Ka is much bigger than 1, we consider it a strong acid, so there isn't any equilibrium. And usually for weak acids, we have a range of 10 to the negative 3 for the K values to 10 to the negative 10th. Monoprotic just means there's one ionizable hydrogen. If it's diprotic, there's two hydrogen ions in the acid formula, and there's triprotic acids which have three ionizable hydrogen atoms. If you look at the K value for an acid that has two hydrogens in it, the first K value, we call that Ka1, that means you're losing the first hydrogen ion in the solution. It's going to be much bigger than the second K value, which is the odds of it losing the second hydrogen ion in the solution. So if you look at this example, this is called sulfurous acid. The K1 value is 1.7 times 10 to the negative 2, and the K2 value for the acid is 6.4 times 10 to the negative 8th. So it's a lot more common for the first hydrogen to be ionized than the second hydrogen to be ionized. If you want the overall K value for both reactions, when you add them up, you would take the Ka times the other Ka. So when you add reactions, just like in the previous chapter 15, you can multiply the K values. Now, as long as the first Ka is more than 1,000 times bigger than the second Ka, you can just worry about the first Ka to determine the pH. Now, since pH gives the equilibrium concentration of hydrogen ions, you could do an icebox and figure out what the Ka value is if you already knew the pH. And we do some practice problems in class. And then I throw in this acid fact. If you have a non-metal oxide, not a metallic oxide now, it's a non-metal oxide, it actually can react with water to form a weak acid. So metallic oxides are basic in water. Non-metal oxides are acidic in water. And sulfur dioxides are in high sulfur coal, and you're not supposed to burn high sulfur coal because then the sulfur dioxide that's released will react with water and then form acid rain. Also, carbon dioxide in the atmosphere naturally reacts with the water vapor in the air to form a slightly acidic carbonic acid solution. So rainwater always has a slight acidity to it because of the carbon dioxide dissolved in the water. But if you want to make the acid rain even worse, then the sulfur dioxides and the nitrogen dioxides that are produced by burning high sulfur coal, or even in gasoline engines, they produce nitrogen oxides as a waste product. That makes the acid rain worse. The other example is P2O5, which is diphosphorus pentoxide. It can react with water to form the weak acid phosphoric acid. Now we have the topic of acid-base properties of salts. So nearly all salts are strong electrolytes, which means when you throw them into water they break apart into their ions 100% of the time. Now, the acid-base properties of salts are a consequence of these ions trying to react with water. Now, many salt ions can react to form either hydroxides or hydrogen ions, and this process of an ion reacting with water is called hydrolysis. So here's an example we've seen before. The acetate ion can react with water and it can form the weak acid acetic acid, and you get some hydroxide ions in the water. So that's why acetate ions are classified as a weak base, because they can undergo hydrolysis and produce some OH ions. So anions from a weak acid are classified as a base. Now, if you're an anion from a strong acid, you can't react with water because there's no way that a chloride ion, which was at the very top of that chart that was on one of the slides, there's no way that the chloride ion can form HCl because it's not going to be in equilibrium. Now, there's some ions that are amphoteric, and again, we've seen this before. We have a hydrogen in the front that could be lost, but it has a negative charge, so it could actually gain some hydrogens as well. So they're amphoteric. Now, all cations, except the ones that are in group 1, that's lithium on down and then calcium on down, are classified as a weak acid because they can react with water to form a weak base, which is again in equilibrium, and you accidentally get some hydrogen ions floating around in the solution. So cations, except the ones in group 1 and 2 that I've mentioned before, are classified as weak acid ions because of this hydrolysis reaction. Now, the pH of a solution can be qualitatively predicted using the following guidelines. Now, what I mean by qualitatively predicted, you can just determine if the pH is going to be higher or lower than 7, if it's going to be slightly acidic or slightly basic. If you have a salt that can be made from a strong acid reacting with a strong base, then that salt is classified as neutral. So here's an example. You have sodium chloride. How can you make sodium chloride? Well, you can react the strong base sodium hydroxide with the strong acid hydrochloric acid, and that makes salt water. And so that salt that you made by combining the strong acid and the strong base is classified as neutral. Here's another example, calcium nitrate. It comes from calcium hydroxide reacting with nitric acid. That strong combination is going to make a neutral salt. Now, what if you had a strong base reacting with a weak acid to make a salt? Well, that strong base reacting with a weak acid is going to be slightly basic. And here's some examples. We have sodium hypochlorite, which is a strong base ion plus a weak acid ion, and that can make a slightly basic solution. And here's another example, barium acetate. Barium acetate can be made from reacting the strong base barium hydroxide with the weak acid acetic acid. And so that combination of barium ions and acetate ions is going to make the solution slightly basic, and we'll look at the reaction why barium acetate is slightly basic in solution on the next slide. Now, if you have a strong acid, weak base combination, then it's going to be slightly acidic. And again, we're going to look at the reaction on the next page, why this happens. So what's happening in the solution that makes these things slightly acidic or slightly basic? So let's break apart barium acetate into its ions. You have barium ions and you have acetate ions. Now, those ions are going to try to undergo hydrolysis. They're going to try to react with water. Now, the first ion is barium. And so when barium tries to react with water, it forms barium hydroxide. But barium hydroxide does not exist in an equilibrium. It's one of our strong bases. So there's no way that barium hydroxide can form. Well, if barium hydroxide can't form, then there's not going to be any hydrogen ions in the solution to make it acidic. So a barium ion, when it's in water, cannot undergo hydrolysis, so it's a neutral ion. Now, the acetate ion, as we've seen many times before, can react with water, and when it does, it forms the weak acid, acetic acid, and it does produce some OH ions in the solution. So it's the acetate ion that makes the solution basic. Now, what about a salt that has a weak combination, a weak acid, weak base combination? Well, then you're going to have to look at the K values. So the ion with the largest ionization constant will have the greatest influence on the pH. So we look at an example. We have the salt ammonium fluoride. And now the Ka value for the ammonium ion is 5.6 times 10 to the negative 10th. The Kb value for the fluoride ion, once it undergoes hydrolysis, is 1.5 times 10 to the negative 11th. So which value is bigger? Well, the Ka value is a little bigger than the Kb value, so this reaction will be slightly acidic, which means there's going to be a little more hydronium ions in the solution than hydroxide ions. Now there are some salts which contain ionizable protons, such as sodium hydrogen carbonate, which is baking soda, or sodium biphosphate, I believe is the name of that compound. And the pHs of these salts is not only affected by hydrolysis, it's also affected by the Ka value, so how much it tends to lose the H's. So there's more complicated examples of this in the textbook, but we just need to worry about the salt combination to see what the strength of the ions were in the water, or whether they can undergo hydrolysis to determine if a solution is going to be acidic or basic. Now we're going to stop the PowerPoint here, and then I'll have a part 2 lecture later on, because this lecture is kind of going longer than the 30 minutes that I typically have. So we're going to stop the lecture here, and we'll continue it in part 2 on factors that affect acid strength.